Hi, I'm back again reading chapter 11. Last time I didn't finish. We're on page 382. If you're continuing from the previous episode, it's just me removing my bookmark from the page. So I'm going to skip over the code and begin with the paragraph on 382. The version without lists required 36 lines of code to accomplish the same task, but we can do even better than this. Notice that this code still uses the if-elif structure to determine which pips should be turned on. Since the correct list of indexes is determined by value, a number between 1 and 6, we could make this decision table-driven instead. The idea is to use a list where each item in the list is itself a list of pip indexes. For example, the item in position 3 should be the list 0, 3, 6, since these are the pips that must be turned on to show a value of 3. Here is how a table-driven approach can be coded. On table equals, open bracket, empty brackets, comma, 3 in brackets, comma, 2, 4 in brackets, comma, 2, 3, and 4 in brackets with commas, comma, new line, open bracket 0, 2, 4, 6, comma, end bracket, comma, open bracket 0, 2, 3, 4, 6, end bracket, comma, open bracket 0, 1, 2, 4, 6, 5, 6, 6, no comma, end bracket, For pip in self.pips, colon, new line, self.pip.setFill, with a capital F, open parentheses, self.background, and parentheses. New line on equals on capital T table, open bracket, value, close bracket. New line for I in on colon, new line, self.pips, I in brackets, dot set fill with a capital F, open parentheses, self.foreground, and parentheses. I have called the table of pip indexes on table with a capital T. Notice that I padded the table by placing an empty list on the first position. If value is 0, then die view will be blank. Now we have reduced our 36 lines of code down to 7. In addition, this version is much easier to modify. If you want to change which pips are displayed for various values, you simply modify the entries in on table. There is one last issue to address. The on table will remain unchanged throughout the life of any particular die view. Rather than recreating this table each time a new value is displayed, it would be better to create the table in the constructor and save it in an instance variable. That's got a footnote on it. An even better approach would be to use a class variable, but class variables are beyond the scope of the current discussion. Putting the definition of on table into underscore underscore in it underscore underscore yields this nicely completed class. Hashtag, new line, hashtag dieview2.py, new line from graphics import asterisk, class dieview colon, open quote, open quote, open quote. Die view is a widget that displays a graphical representation of a standard 6-sided die, period, end quote, end quote, end quote. New line, def, underscore, underscore, init, underscore, underscore, open parentheses, self, comma, win, comma, center, comma, size, end parentheses, colon. New line, open quote, open quote, open quote, create a view of a die, comma, E period G period colon, new line, D1 equals G die, open parentheses, my win, comma, point, open parentheses, 40, comma, 50, end parentheses, comma, 20, end parentheses. New line creates a die centered at, open parentheses, 40, comma, 50, end parentheses, having sides of length 20, period, end quote, end quote, end quote. New line, hashtag, first define some standard values. New line, self dot win equals win. New line, self dot background equals quote white end quote, hashtag color of die face. New line, self dot foreground equals in quotes black, hashtag color of the pips. New line, self dot p size equals 0.1 asterisks asterisk 1. There's only one asterisk. Size, hashtag radius of each pip. New line, h size equals size slash 2.0, hashtag half of size. New line, offset equals 0.6, 1 asterisk. H size, hashtag distance from center to outer pips. New line, hashtag create a square for the face. New line, cx, cy equals center dot get x, empty parentheses, comma, center dot get y, empty parentheses. New line, p1 equals point, open parentheses, cx dash h size, comma, cy dash h size, end parentheses. New line, p2 equals point, open parentheses, cx plus h size, comma, cy plus h size, end parentheses. New line, rect equals rectangle with a capital R, open parentheses, p1, comma, p2, end parentheses. New line, rect dot draw, open parentheses, win, end parentheses. New line, rect dot set fill with a capital F, open parentheses, self dot background, end parentheses. New line, hashtag create 7 circles for standard pip locations. New line, self dot pips equals open bracket self dot underscore underscore make pip with a capital P in the beginning of pip. I don't know if I need to keep saying that. Open parentheses, cx dash offset, comma, cy dash offset, end parentheses, comma, new line, self dot underscore underscore make pip, open parentheses, cx dash offset, comma, cy, end parentheses, comma, new line, self dot underscore underscore make pip, open parentheses, cx dash offset, comma, cy plus offset, end parentheses, comma, new line, self dot underscore underscore make pip, open parentheses, cx, comma, cy, end parentheses, comma, new line, self dot underscore underscore make pip, open parentheses, cx plus offset, comma, cy dash offset, end parentheses, comma, new line, self dot underscore underscore make pip, open parentheses, cx plus offset, comma, cy, end parentheses, comma, new line, self dot underscore underscore make pip, open parentheses, cx plus offset, comma, cy plus offset, end parentheses, end bracket. New line, hashtag create a table for which pips are on for each value, self dot on table equals open bracket, empty brackets, comma, 3 in brackets, comma, open bracket 2, comma, 4 end bracket, comma, open bracket 2, comma, 3, comma, 4 end bracket, comma, open bracket 0, comma, 2, comma, 4, comma, 6 end bracket, comma, open bracket 0, comma, 2, comma, 3, comma, 4, comma, 6 end bracket, comma, open bracket 0, comma, 1, comma, 2, comma, 4, comma, 5, comma, 6 end bracket, end bracket. New line, self dot set value with capital V and a 1 in parentheses. New line, def underscore underscore make pip, open parentheses, self, comma, x, comma, y, end parentheses, colon, new line, open quote, open quote, open quote, internal helper method to draw a pip at, open parentheses, x, comma, y, end parentheses, end quote, end quote, end quote. New line, pip equals circle, open parentheses, point, open parentheses, x, comma, y, end parentheses, comma, self dot p size, end parentheses. new line pip.setFill, open parentheses, self.background, end parentheses, new line pip.setOutline, open parentheses, self.background, end parentheses, new line pip.draw, open parentheses, self.win, end parentheses, new line return pip, new line def set value, open parentheses, self comma value, end parentheses, colon, new line, open quote, set this die to display value, period, end quote, new line, hashtag, turn all the pips off. For pip in self.pips, colon, new line, pip.setFill, open parentheses, self.background, end parentheses, new line, hashtag, turn the appropriate pips back on. For I in self.onTable, open bracket, value, close bracket, colon, new line, self.pips, I in brackets, dot set fill, open parentheses, self.foreground, end parentheses. All right. This example also showcases the advantages of encapsulation that I talked about in Chapter 10. We have significantly improved the implementation of the die view class, but we have not changed the set methods that it supports. We can substitute this improved version into any program that uses a die view without having to modify any of the other code. The encapsulation of objects allows us to build complex software systems as a set of quote-unquote pluggable modules. Section 11.5, Case Study, Python Calculator. The reworked die view class shows how lists can be used effectively as instance variables of objects. Interestingly, our pips list and onTable list contain circles and lists, respectively, which are themselves objects. By nesting and combining collections and objects, we can devise elegant ways of storing data in our programs. We can even go one step further and view a program itself as a collection of data structures, or collections and objects, and a set of algorithms that operate on those data structures. Now, if a program contains data and operations, one natural way to organize the program is to treat the entire application itself as an object. New section 11.5.1. A calculator as an object. As an example, we'll develop a program that implements a simple Python calculator. Our calculator will have buttons for the 10 digits, 0 through 9, a decimal point, the 4 operations, plus, minus, asterisk for multiplication, and a slash for division, and a few special buttons. C to clear the display, less than with a dash to backspace over characters in the display, and an equal sign to do the calculation. We'll take a very simple approach to performing calculations. As buttons are clicked, the corresponding characters will show up in the display, allowing the user to create a formula. When the equal key is pressed, the formula will be evaluated and the resulting value shown in the display. Figure 11.1 shows a snapshot of the calculator in action. Basically, we can divide the functioning of the calculator into two parts, creating the interface and interacting with the user. The user interface in this case consists of a display widget and a bunch of buttons. We can keep track of these GUI widgets with instance variables. The user interaction can be managed by a set of methods that manipulate the widgets. To implement this division of labor, we will create a calculator class that represents the calculator in our program. The constructor for the class will create the initial interface. We will make the calculator respond to user interaction by invoking a special run method. Section 11.5.2, constructing the interface. Let's take a detailed look at the constructor for the calculator class. First, we'll need to create a graphics window to draw the interface. Figure 11.1, Python calculator in action. I will show you the image on page 386. It looks a lot like a little pocket calculator. So continuing on, we have code. Def __ init __ open parentheses self close parentheses colon new line hashtag create the window for the calculator new line win equals graph win open parentheses open quote calculator end quote end parentheses new line win dot set chords open parentheses 0, 0, 6, 7, end parentheses, new line win dot set background, open parentheses, open quote slate gray, end quote, end parentheses, new line self dot win equal win. The coordinates for the window were chosen to simplify the layout of the buttons. In the last line, the window object is tucked into an instance variable so that other methods can refer to it. The next step is to create the buttons. We will reuse the button class from the previous chapter. Since there are a lot of similar buttons, we will use a list to store them. Here is a code that creates the button list. Hashtag create list of buttons. Hashtag start with all the standard sized buttons. Hashtag bspecs gives center chords and label of buttons. New line bspecs equals these coordinates, and I am not going to read all this. You can look at the book and follow along for all of the coordinates of all of the buttons that are going to go onto the calculator. New line self dot buttons equals empty brackets. And on the next page, we have 4 open parentheses cx, cy, label, end parentheses in bspecs, colon, new line self dot buttons dot append, open parentheses button, open parentheses self dot win, point, open parentheses cx, cy, end parentheses, 0.75, 0.75, label, end parentheses, new line hashtag create the larger equal in single quotes button, new line self dot buttons dot append, open parentheses button, open parentheses self dot win, point, open parentheses 4.5, 1, end parentheses, 1.75, 0.75, equal in quotes, end parentheses, new line, hashtag activate all buttons, new line 4b in self dot buttons, colon, new line b dot activate, empty parentheses. Study this code carefully. A button is normally specified by providing a center point width, height, and label. Typing out calls to the button constructor with all this information for each button would be tedious, I believe. Rather than creating the buttons directly, this code first creates a list of button specifications, the bspecs. This list of specifications is then used to create the buttons. That's smart. It's like copy and paste. Each specification is a tuple consisting of the x and y coordinates of the center of the button and its label. A tuple looks like a list except that it is enclosed in round parentheses instead of in square brackets. A tuple is just another kind of sequence in Python. Tuples are like lists, except the tuples are immutable. The items can't be changed. If the contents of a sequence won't be changed after it is created, using a tuple is more efficient than using a list. The next step is to iterate through the specification list and create a corresponding button for each entry. Take a look at the loop heading. For open parentheses cx, cy, label, end parentheses in bspecs, colon. According to the definition for a loop, the tuple, open parentheses cx, cy, label, end parentheses, will be assigned each successive item in the list bspecs. Put another way, conceptually, each iteration of the loop starts with an assignment. Cx, Cy, label equals next item from bspecs. Of course, each item in bspecs is also a tuple. When a tuple of variables is used on the left side of an assignment, the corresponding components of the tuple on the right side are unpacked into the variables on the left side. In fact, this is how Python actually implements all simultaneous assignments. The first time through the loop, it is as if we had done this simultaneous assignment. Cx, Cy, label equals 2, 1, 0 in quotes. Each time through the loop, another tuple from bspecs is unpacked into the variables in the loop heading. The values are then used to create a button that is appended to the list of buttons. After all the standard size buttons have been created, the larger equal button is created and tacked onto the list. Self.buttons.append, open parentheses, button, open parentheses, self.win, point, open parentheses, 4.5, 1, end parentheses, 1.75, 0.75, and then equals in quotes, end parentheses, end parentheses. I could have written a line like this for each of the previous buttons, but I think you can see the appeal of the specification list/loop approach for creating the 17 similar buttons. In contrast to the buttons, creating the calculator display is quite simple. The display will just be a rectangle with some text centered on it. We need to save the text object as an instance variable so that its contents can be accessed and changed during the processing of button clicks. Here is the code that creates the display. All right, here we go. We're coding. BG equals rectangle, open parentheses, point, open parentheses, 0.5, 5.5, end parentheses, point, open parentheses, 5.5, 6.5, end parentheses, new line, bg.setFill, open parentheses, open single quote, white, end single quote, end parentheses. New line, bg draw, open parentheses, self.win, end parentheses. New line, text equals text, open parentheses, point, open parentheses, 3, 6, end parentheses, empty quotes, end parentheses. New line, text dot draw, open parentheses, self dot win, end parentheses. New line, text dot set face, open parentheses, open quote, courier, end quote, end parentheses. New line, text dot set style, open parentheses, open quote, bold, end quote, end parentheses. New line, text dot set size, open parentheses, 16, end parentheses. New line, self dot display equals text. All right, new section of the chapter 11.5.3, processing buttons. Now that we have an interface drawn, we need a method that actually gets the calculator running. Our calculator will use a classic event loop that waits for a button to be clicked and then processes that button. Let's encapsulate this in a method called run. Def run, open parentheses, self, close parentheses, colon, new line, while true with a capital T, colon, new line, key equals self dot get key press, empty parentheses, new line, self dot process key, and then in parentheses key. Notice that this is an infinite loop. To quit the program, the user will have to quote unquote kill the calculator window. All that's left is to implement the get key press and process key methods. Getting key presses is easy. We continue getting mouse clicks until one of those mouse clicks is on a button. To determine whether a button has been clicked, we loop through the list of buttons and check each one. The result is a nested loop. Here we go. Def get key press, open parentheses, self, close parentheses, colon, new line, Hashtag waits for a button to be clicked. New line. Hashtag returns the label of the button that was clicked. New line. While true with a capital T, colon. New line. Hashtag loop for each mouse click. New line. P equals self.win.getMouse, empty parentheses. New line. For B in self.buttons, colon. New line. Hashtag loop for each button. New line. If B.clicked, open parentheses, P, end parentheses, colon, new line, return B.getLabel, empty parentheses, hashtag method, exit. You can see how having the buttons in a list is a big win here. We can use a for loop to look at each button in turn. If the clicked point, P, turns out to be one of the buttons, the label of that button is returned, providing an exit from the otherwise infinite while loop. The last step is to update the display of the calculator according to which button was clicked. This is accomplished in process key. Basically, this is a multi-way decision that checks the key label and takes the appropriate action. A digit or operator is simply appended to the display. If key contains the label of the button and text contains the current content of the display, the appropriate line of code looks like this. Self.display.setText, open parentheses, text plus key, end parentheses. The clear key blanks the display. Self.display.setText, open parentheses, empty quotes, end parentheses. New line. Well, this isn't code. The backspace strips off one character. Self.display.setText, open parentheses, text, open bracket, colon, -1, end bracket, end parentheses. Finally, the equal key causes the expression in the display to be evaluated and the result displayed. New line, try, colon, new line, result equals eval, and then text in parentheses. New line, accept, colon, new line, result equals single quote, error, all in caps, and single parentheses. New line, self.display.setText, open parentheses, str, open parentheses, result, end parentheses, end parentheses. The try-except statement here is necessary to catch runtime errors caused by entries that are not legal Python expressions. If an error occurs, the calculator will display error rather than causing the program to crash. Here is a complete program. I really think that you should read this in your book. I don't feel like I need to read all of this out. There are the coordinates for the buttons, and there are the displays, and there are the functions. And when we get to the end on page 392 of all of that coding, it says, notice especially the very end of the program. To run the application, we create an instance of the calculator class and then call its run method. All right, section 11.6. Here's a case study, a better cannonball animation. The calculator example used a list of button objects to simplify the code. In this case, maintaining a collection of similar objects as a list was strictly a programming convenience, as the contents of the button list never changed. Lists or other collection types become essential when the collection changes dynamically during program execution. Consider the cannonball animation from the last chapter. As we left it, the program could show only a single shot at a time. In this section, we will extend the program to allow multiple shots. Doing this requires keeping track of all the cannonballs currently in flight. That's a constantly varying collection, and we'll use a list to manage it. Section 11.6.1. creating a launcher. Before jumping into the use of a list to animate multiple shots, we need to update the program's user interface a bit so that firing multiple shots is feasible. In the previous version of the program, we got information from the user via a simple dialog window. For this version, we want to add a new widget that allows the user to rapidly fire shots with various starting angles and velocities, more like a video game. The launcher widget will show a cannonball ready to be launched, along with an arrow representing the current settings for the launch angle and the velocity. Figure 11.2 shows the animation with the launcher at the left edge and multiple shots in flight. The angle of the arrow indicates the launch direction, and the length of the arrow represents the initial speed. Mathematically inclined readers might recognize the arrow as the standard vector representation of the initial velocity. The entire simulation will be under keyboard control, with keys assigned to increase or decrease the launch angle, increase or decrease the speed, and fire the shot. So here we have the illustration, figure 11.2, enhanced cannon animation. That should match what I was just describing in the reading. You see the arrow and the cannonballs in motion, and you can follow along with it in your book on page 393. And now the next page. We start by defining a suitable class describing the behavior of a launcher. A launcher will obviously need to keep track of a current angle and velocity. Let's use instance variables self.angle and self.vel, or velocity, for these values. We have to decide on units of measurement for these. The obvious choice for velocity, sorry, there's a pop-up, for velocity is meters per second, since that is what the projectile class uses. For the angle, either degrees or radians is a reasonable choice. Internally, it's most efficient to work with radians, since that is what the Python library uses. For passing values in, degrees are useful as they are more intuitive for most programmers. I agree. The constructor for the class will be the hardest method to write, since it draws the launcher and initializes all the instance variables. Let's write some other methods first to gain insight into what the constructor will have to accomplish. First up, we need mutator methods to change the angle and velocity. When we press a certain key, we want the angle to increase or decrease a fixed amount. The exact amount of change is up to the interface, so we will pass that as a parameter to the method. When the angle changes, we will also need to redraw the launcher to reflect that new value. Here's a suitable method. Class launcher, new line, def, angle, open parentheses, self.amt, end parentheses, new line, open quote, open quote, change launch angle by AMT degrees, end quote, end quote, end quote. New line, self.angle equals self.angle plus radians, and then AMT in parentheses. New line, self.redraw, empty parentheses. Notice that the redrawing is done by a separate, as yet unwritten, method. Since adjusting the velocity will also require redrawing, it makes sense to factor this operation out into a helper method. You can also see that the amount of adjustment, AMT, is converted from degrees to radians and simply added to the existing value. Positive values will raise the launch angle, and negative values will decrease it. Following the same pattern, we can easily write a method for adjusting the velocity. Here we go. Def, adjvel, new open parentheses, self.amt, end parentheses, new line, open quote, open quote, open quote, change launch velocity by AMT, end quote, end quote, end quote. New line self.vel equals self.vel plus AMT. New line self.redraw empty parentheses. As with the adj angle, we can use positive or negative values of AMT to increase or decrease the velocity respectively. To complete these two methods, we need to supply the redraw method. What does it do? It should undraw the current arrow and then use the values of self.angle and self.vel to draw a new one. But what is an arrow? It's really just a line. If you look back at the documentation for the line class at the end of chapter 4, you'll see that you can use the set arrow method to put an arrowhead at either or both ends of a line. Now, in order to undraw an arrowhead at undraw the previous line or arrow, we'll need an instance variable that stores it so that we can ask it to undraw itself. Let's call that instance variable self.arrow. Using this insight, along with a bit of trigonometry for getting the x and y components of the velocity, that's covered in section 10.2, our redraw method looks like this. Here we go. Def redraw, open parentheses, self, end parentheses, colon, new line, open quote, open quote, open quote. Redraw the arrow to show current, angle, and velocity, end quote, end quote, end quote. New line, self.arrow.undraw, empty parentheses. New line, part 2, or PT.2, PT2, equals point, open parentheses, self.vel asterisk, cos, C-O-S, open parentheses, self.angle, end parentheses, comma, self.vel asterisks, sine, S-I-N, open parentheses, self.angle, end parentheses, end parentheses. New line, self.arrow equals line, open parentheses, point, open parentheses, 0, comma, 0, end parentheses, comma, PT2, end parentheses, dot, draw, open parentheses, self.win, end parentheses. Self, new line, self.arrow.set arrow, open parentheses, open quote, last, end quote, end parentheses. New line, self.arrow.set width, open parentheses, 3, end parentheses. This code undraws the existing line stored in the instance variable self.arrow and then creates a new one. You can see that the start of the arrow is always at 0, 0, with the endpoint determined by the angle and velocity. The new line is created, drawn, and then saved into the instance variable. Calling set arrow, open parentheses, quote unquote last, end parentheses, is what causes the line to have an arrowhead at the second point. We also need a method to fire a shot from the launcher. Remember, we already designed a shot tracker class back in chapter 10, so we can reuse that class to create a suitable shot. A shot tracker requires window, angle, velocity, and height as parameters. The initial height will just be 0, and the angle and velocity are instance variables. But what about the window? We do not want to create a new window. We want to use the existing window where the launcher is drawn. That means we need another instance variable, self.win. With that assumption, the method practically writes itself. He's funny. Here we go. Def fire, self inside parentheses, colon, new line. Return, shot tracker, open parentheses, self.win, comma, degrees, open parentheses, self.angle, end parentheses, comma, self.vel, comma, 0.0, end parentheses. Notice that the method simply returns an appropriate shot tracker object. It will be up to the interface to actually animate the shot. The fire method is not the appropriate place for the animation loop. Do you see why? Here's a hint. Should launcher interactions be modal All we have left is writing a suitable constructor. It needs to draw the base cannonball, initialize the instance variables, win, angle, vel, and arrow, and call redraw to make the correct arrow show up. Here's the code. Def underscore underscore init underscore underscore open parentheses self comma win end parentheses colon new line hashtag draw the base shot of the launcher new line base equals circle open parentheses point open parentheses 0 comma 0 end parentheses comma 3 end parentheses new line base dot set fill open parentheses open quote red end quote end parentheses new line base dot set outline open parentheses open quote red close quote end parentheses new line base dot draw open parentheses win end parentheses new line hashtag save the window and create initial angle and velocity new line self.win equals win self.angle equals radians open parentheses 45.0 end parentheses new line self.vel equals 40.0 new line hashtag create initial quote unquote dummy arrow needed by redraw new line self.arrow equals line open parentheses point open parentheses 0 comma 0 end parentheses comma point open parentheses 0 comma 0 end parentheses dot draw open parentheses win end parentheses new line hashtag replace it with the correct arrow new line self dot redraw and empty parentheses new section 11.6.2 tracking multiple shots. With the launcher in hand, we can turn to the interesting issue in this program, namely having multiple things happening at the same time. We want to be able to adjust the launcher and fire more shots while some shots are still in the air. In order for that to happen, the event loop that monitors keyboard input has to run to keep interaction active while the cannonballs are flying. Essentially, our event loop has to do double duty, also serving as an animation loop for all the shots that are currently quote unquote alive. The basic idea is to have the event loop go around at a decent rate for animation, say 30 iterations per second, and each time through the loop, we move all the shots that are in flight and also perform any action requested by the user. Given the complexity of this program, it is probably a good idea to proceed as we did with the calculator example and create an application object. I'll call it Projectile App. The class will contain a constructor that draws the interface and initializes all the necessary variables, as well as a run method to implement the combined event animation loop. Here's the beginning of the class with a suitable constructor. Here we go with the coding. Class projectile app, new line, def underscore underscore init underscore underscore self in parentheses and a colon. New line, hashtag create graphics window with a scale line at the bottom. New line, self.win equals graph win, open parentheses, open quote, projectile animation, end quote, comma, 640, comma, 480, end parentheses. New line, self.win.set chords, new parentheses, -10, comma, -10, comma, 210, comma, 155, end parentheses. New line, open parentheses, point, open parentheses, -10, comma, 0, end parentheses, comma, point, open parentheses, 210, comma, 0, end parentheses, dot, draw, open parentheses, self dot win, end parentheses. New line, 4x in range, open parentheses, 0, comma, 210, comma 50, end parentheses, colon, new line, text, open parentheses, point, open parentheses, x, comma, -7, end parentheses, comma, str, open parentheses, x, end parentheses, dot, draw, open parentheses, self dot win, end parentheses, new line, open parentheses, point, open parentheses, x, comma, 0, end parentheses, comma, point, open parentheses, x, comma, 2, end parentheses, dot, draw, open parentheses, self dot win, end parentheses, new line, hashtag, add the launcher to the window, new line, self dot launcher equals launcher, in parentheses, self dot win, new line, hashtag, start with an empty list of quote unquote live shots, new line, self dot shots equals empty brackets. The code for creating the animation window is just like it was in the previous version of the program. The lines at the bottom of the method add new instance variables for the launcher and the list of live shots that are being animated. Here is the run method implementing the event animation loop. Here's the coding. Def run, open parentheses, self, end parentheses, colon, new line, hashtag, main event / animation loop, new line, while true with a capital T, colon, new line, self dot update shots, open parentheses, 1/30, end parentheses, new line, key equals self dot win dot check key, empty parentheses, new line, if key in open bracket, Q in quotes, comma, capital Q in quotes, end bracket, colon, new line, break. New line, if key equals up in quotes, colon, new line, self dot launcher dot edge angle, 5 in parentheses, new line, L if key equals quote unquote down, colon, new line, self dot launcher dot edge angle, open parentheses, -5, close parentheses, new line, elif key equals right in quotes, colon, new line, self dot launcher dot adjvel, 5 in parentheses, new line, elif key equals left in quotes, colon, new line, self dot launcher dot adjvel, open parentheses, -5, end parentheses, new line, elif key in open bracket, F in quotes, comma, capital F in quotes, end bracket, colon, new line, self dot shots dot append, open parentheses, self dot launcher dot fire, empty parentheses, end parentheses, new line, update, 30 in parentheses, new line, self dot win dot close, empty parentheses. There is not really much to this loop. The first line invokes a helper method that moves all of the live shots. We still have to write that one, but the intent is pretty obvious. It's the animation portion of the loop. The rest of the loop handles keyboard events. We use check key, ensuring that the loop keeps going around to keep the shots moving even when no key has been pressed. The up, down, left, and right key designations refer to the corresponding arrows on the keyboard. Up and down are used to change the launcher angle, while left and right alter the launcher velocity. Do you see how easy it is to actually fire a cannonball? When the user hits the F key, we get a shot tracker object from the launcher and simply add this to the list of live shots. The shot tracker created by the launcher's fire method is automatically drawn in the window, and adding it to the list of shots via self.shots.append ensures that its position changes each time through the loop due to the update shots call at the top. The last line of the loop ensures that all of the graphics updates are drawn and serves to throttle the loop to a maximum of 30 iterations per second, thus matching the time interval, 1 out of 30, used in the call at the top of the loop. Again, you can play with those two values to alter the apparent speed of the animation. Finally, we are left with the writing the update shots method that handles the animation of shots. This method has two jobs: moving all of the live shots and updating the list to remove any that have died, either have landed or flown horizontally out of the window. The second task keeps the list trimmed to just the collection of shots that need animating. The code to do the first task is straightforward. We just need to loop through the list of shot tracker objects and ask each one to update. Something like this would do the job. So here's the programming. Def, update shots, open parentheses, self, comma, dt, end parentheses, colon, new line, for shot in self.shots, colon, new line, shot.update, open parentheses, dt, end parentheses. We are on page 399, and I'm going to need to stop there once again and continue this video later. It's almost an hour, and I've run out of time once again. See you in the next one. Bye.